Welcome back to today's session. In the previous sessions, we have seen how to solve a transportation problem for its IBFS. We have also seen the different cases like maximization case and the unbalanced transportation problems. We've also learned optimization using Modi method. Today, we'll be dealing with degeneracy in transportation problem. So, what is degeneracy and how to handle degeneracy is what we will be dealing in today's session. See, if the number of non negative independent allocations or the assignments that you have made in the transportation problem is less than m plus n minus 1, then it indicates degeneracy. That means then the degeneracy exists. This situation may occur either in the initial stage of your optimization, that is, in the IBFS itself, you might encounter this, or in the later or the subsequent iterations, you might encounter. So that means to say, after every iteration, when you get a new transportation solution, you are supposed to check for degeneracy case. So to resolve degeneracy, we need to do the following steps. Among the empty cells or among the non-allocated cells, choose an empty cell having least cost. Out of all the non-allocated cells, pick one cell which has the least cost, which is of an independent position. If you have more than one such cells which has a minimum cost, then arbitrarily you can select any one of them, right? If this condition is found in more than one cell, choose any one arbitrarily. So you have chosen one cell in step 1. To that particular cell chosen in step 1, allocate a small positive quantity epsilon, which is just greater than 0. Once again, I'm telling you, we are making an assignment of a very small, negligible positive quantity called epsilon. It is just greater than 0. So it is very negligible quantity, but it has to be a positive quantity. Clear? The cells containing epsilon are treated like any other occupied cell and the degeneracy is removed. So once you make an additional, allocation, the degeneracy scenario is lost, it becomes a non-degenerate case. You can continue solving the problem or continue optimizing using Modi method, right? For this modified solution, adopt the steps involved in Modi method till an optimal solution is obtained, right? This is how degeneracy is handled in transportation problem. So to understand this very clearly in a better way, so what we do is we try to solve a problem. So consider a problem, obtain the IBFS of the transportation problem using NWCR and optimize the same using Modi method. The cost matrix is given below. So because they have specified cost matrix, it is a minimization case. Fine. And now what next you are supposed to do is check whether it is balanced or not. So add up the supplies, 10 plus 15, 25, 25 plus 40, 65. Add up the demands, 20 plus 15, 35, 35 plus 30, 65. So both the supplies and demand matches. So it is a balanced transportation problem. So the cost matrix given to us is 2, 2, 3, 4, 1, 2, 1, 3 and 1. Fine. So first thing that we are supposed to do is check whether it is a balanced transportation problem or not. So because both the totals match and it is 65, it is a balanced transportation problem. So we go about solving it. we try to solve the IBFS. So they have specified to solve it using NWCR. So the top left corner has to be chosen. So the top left corner is O1 D1. So you make an allocation here. So how much allocation can be made? Supply is 10, demand is 20, you can satisfy 10. So you make an allocation of 10 so that the supply becomes 10 minus 10, 10 minus 10, 0. The supply becomes 0, demand becomes 20 minus 10, 10, right? So you make an allocation of 10 units across 1 comma 1, 1 comma 1, 10 units. So this row is gone. So now out of the remaining matrix, which is the top left corner or the northwest corner, so O2 D1. So here we are supposed to make an allocation. Demand is 10, supply is 15, so you can satisfy 10. So I will get supply as 15 minus 10, 5, demand as 10 minus 10, 0. So I get an allocation at 2 comma 1 with 10 units. So the first row is gone and the first column is gone now. Now the remaining matrix is 1, 2, 3, 1. So in this northwest corner or the top left corner is O2 D2. Okay, here I am supposed to make an allocation. Supply is 5, demand is 15. So I can satisfy 5. So the supply becomes 5 minus 5, 0. Demand becomes 15 minus 5, 10. So I get an allocation of 5 units across 2 comma 2. So 2 comma 2, 5 units. So first row is gone. Second row is also gone. First column is also gone. Now I am left out with only these two elements. So in this, the top left corner is obviously O3D2. So here I am supposed to make an allocation. How much? Demand is 10, supply is 40. So you can satisfy only 10 units. So demand becomes 10 minus 10, 0. Supply becomes 40 minus 10, 30. So I get an allocation of 10 units across 3 comma 2. So the first row is gone now. Second row is also gone. First column is gone. Second column is also gone. I am left out with only a single cell. So when I am left with a single cell, obviously the demand and the supply should match. So the demand is 30, supply is also 30. So satisfy 30 so that this row and this column will be gone. Fine. So the IBFS that I get, oh sorry, one small mistake here. This 10 is not there. So the supply and, the IBFS is 10 across 1 comma 1, 10 across 2 comma 1, 5 across 2 comma 2, 10 across 3 comma 2, and 30 across 3 comma 3. So the total transportation cost will be 10 into 2 plus 10 into 4 plus 5 into 1 plus 10 into 3 plus 30 into 1. So 20, 10 into 2 is 20, 10 into 4 is 40, 5 into 1 is 5, 10 into 3 is 30, 30 into 1 is 30. So when you add up all this, 20 plus 40, 60, 60 plus 5, 65, 65 plus 30, 95, 95 plus 30, 125. So the TTC is 125 for the IBFS. Now check for the degeneracy case. How many allocations you have? 1, 2, 3, 4, 5. I have 5 allocations. And how much I am supposed to have? M plus N minus 3. M is the number of rows. I have 3 rows. N is the number of columns. I have 3 columns. So 3 plus 3, 6. 6 minus 1 is 5. So I am supposed to have 5 allocations. I have 5 allocations. So the problem is at the non-degeneracy case in this particular level. So at this particular stage, it is in non-degeneracy case. So go about optimizing it. So how do we go about optimizing? Find out the UI and VJ values. Let me consider this row UI value as 0. right? So using these two as reference value, I get the Vj values as 4 and 1. Okay. Now I'll take this as a reference. I take this as a reference. So this becomes the corresponding reference value. 2 minus 4 becomes minus 2. Okay. So now I'll take this as the reference value, 1 as the reference value. So here, this becomes the key cell or the key value. 3 minus 1 is 2. Okay. Now all the UI values have been found out. Now consider this 2 as a reference. So I'll consider this 2 as a reference. This becomes the key value. 1 minus 2 is minus 1. So all UI and Vj values are computed. What next? We are supposed to find out the net evaluations, Eij values. So I'll get Eij values at 1 comma 2. So which will be 2 minus of minus 2. 2 plus 2, 4. 4 minus 1 will be 3. So I get a 3 here. Then here 3 minus of minus 2. 3 plus 2 is 5. 5 minus of minus 1. I get a 6 here. Then I will get a Eij value here. 2 minus 0 is 2. Minus of minus 1, it becomes 3. So I get a 3 here. Next, at this place, 1 minus 2 is minus 1. Minus 1 minus 4 is minus 5. I get a negative value minus 5 here. Fine. So I get only one negative value minus 5. 3, 6, 3 and a minus 5 are the Eij values. So pick the most negative Eij position. So that will be my first point, and using that construct a loop. So I take this as continuation point. From here I will move to this particular place, and from here I will move to this place and back to the starting point. So closed loop is obtained. So now wherever I have, alternating signs have to be put. So in the first place I put a plus sign. Here I get a minus. Here I get a plus. Here I get a minus. So theta value will be the minimum of the allocations at minus theta positions. So at minus positions I have 10 and 10 as the allocations. So check it out. Theta is equal to min of 10 comma 10. So minimum of 10 comma 10 is 10 only. So what happens? So that has to be added wherever I have plus. Here there was no allocation. That means it was 0. So 0 plus 10. Here it becomes a 10. So that 10 is subtracted here. This becomes a 0. No allocation here. Here I will get plus 10. So 5 plus 10, 15. Here I get an allocation 15. Here that 10 is subtracted. So it will become 0. So the allocations will become 10 at this place, 0 at this place, 15 at this place and 0 at this place. See? So I get 10 here, I get a 0 here, 15 here and a 0 here. Okay? Now recheck for degeneracy case. So how many allocations I have? 4 allocations. How many I was supposed to have? 3 plus 3 minus 1, 5. So I was supposed to have 5, but I have only 4 allocations. So the problem is now attained the degeneracy case. So I need to move it from degeneracy case to non-degeneracy case. So for that I need to make an allocation of epsilon. Where should I make? Out of the non-occupied cells. Non-occupied cells are 2, 3, 4, 2 and 3. Out of all this, which is the minimum cost? 2. So I am supposed to make an epsilon allocation at this place. At 1 comma 2, which has a minimum cost of 2, I need to make an allocation of epsilon. See, I make an allocation of epsilon here. So now this has become a non-degeneracy scenario. Once it becomes a non-degeneracy scenario, you can continue solving like your regular solution. Apply Modi method. So I consider this row as 0. So these two becomes reference values, 1 minus 0, 1 and 1 minus 0, 1. Okay. Now use this as reference and this becomes the key value 2. 2 minus 1 becomes a 1. So now use this 1 as reference. This becomes the key value. 2 minus 1 is 1. So I get a 1 here. So now take this 1 as the key reference. So this becomes the key value. 1 minus 1 becomes a 0. So all ui and vj values are evaluated. What next? You're supposed to find out the eij values at non-occupied positions. So what will be the eij values? We will just have a look. 3 minus 1 is 2. 2 minus 1, 1. I get a 1 here. Here, 4 minus 0 is 4. 4 minus 1 is 3. I get a 3 here. At this place, 2 minus 0 minus 1 is a 1. Here, 3 minus 0 minus 1 will be a 2. So I get all positives. So 1, 1, 3, 2, all positives. So as all eij values are positive, the optimal solution is obtained. And none of them are equal to 0. Therefore, it is a unique solution as well. So compute the TTC for this. So the total transportation cost will be 10 into 2 plus epsilon into 2 plus 15 into 1 plus 10 into 1 plus 30 into 1. So 10 into 2 is 20, epsilon into 2 is 2 epsilon, 15 into 1 is 15, 10 into 1 is 10, 30 into 1 is 30. So add up all this, 20 plus 15, 35, 35 plus 10, 45, 45 plus 30, 75. So it will be 75 plus 2 epsilon. As I said, epsilon is a very small negligible value. So this negligible value, when it is multiplied with the least cost, see, epsilon is allocated in the available least cost. So when a very small value is multiplied with a very small value, it remains a very small value. So it still remains a negligible value. So this value 2 epsilon can be ignored, can be negligible, it can be neglected. So your answer will be 75. Okay? Hope you have understood handling the degeneracy case in transportation problem. Hope you people have understood it properly. If at all you have not understood, kindly mention in the comment section if at all you want me to solve one more problem on degeneracy case. If you want me to solve one more problem, in tomorrow's session, I'll be solving one more problem on degeneracy case. Thank you. Thank you for your patient listening. Kindly, as much as possible, stay at home and stay safe. Thank you. Have a nice time. Enjoy.